Okay, so data visualization. So we talked about types of variables. Now we're going to go from there to how do we describe, especially visually, those particular variables. So we're going to focus on categorical variables and then move to quantitative. So visualizing data, the distribution, it describes what values it takes on and how often it takes them. So what was observed and how often was it observed. And graphs or plots, we use it fairly interchangeably. We use these to explore the data. They help us get a snapshot, like, hey, what does it look like? Can I see like that there's a lot more in one group than the other? That kind of idea. People tend to be very visual. I have done a number of consulting projects over the years, and just inevitably people will flip to the page with the plots. Plots definitely tell a lot of what's going on. So the plots you choose and how you use them, absolutely very important. So if we have a quantitative variable, so remember it's numeric and it makes sense to take an average there. They're going to be, there are so many different displays we could use. We're going to focus on histograms, stem plots, and box plots. But no, it goes on and on and on. Every time you think you've heard them all, like, oh, well, here's a violin plot. Oh, here's a density plot. Here's a dot plot. I mean, we tend to be very basic in our naming of them, but we're very prolific. Like, we have a lot of ways to display quantitative data. And then if we have categorical, though, we have two main plots that we tend to use. We tend to prefer the bar plot or bar chart, whichever, and then there are pie charts. Pie charts are pretty common, but I'll poke at why we aren't as big of fans of them for sure. So focusing on categorical data first. So I might have a categorical variable that I'm collecting. So I'll have a sample and I might say, okay, well, out of all the students in my 314 class today, what proportion of them are left-handed? That kind of thing. So sample proportion is p hat. So remember, a hat means I was calculated using sample information. So it'll be the count of successes, and I like to put these in quotes because definition of successes can be very, very relative. So here me saying left hand is not very big deal, but then somebody might want a proportion of cancer patients that die in the first year. We would consider that as a success because the condition we're interested in is present, not because it's actually a good thing per se. So, and then all that all over the sample size. So one way we often display this is we will put it into a frequency table. So we'll put the categories and then we'll either put the counts in each category and or the percent or proportion in each category. So count's pretty common, percent or proportion is also pretty common. So this particular example, we took a random sample of 111 college level intro stats for engineers course students, and we sampled to see what type of software was used in the course. I'm not sure. It's probably not just one university. It sounds like it's across many. So like out of the 111, 34 of those students used R in their stats engineering course, and so on. So things to note too, if I were to add the counts up, they should add to 111 because that was my total sample size. And then similarly, the percent should add up to 100%. Sometimes they don't add up to exactly 100%, but really darn close. That's going to come down to rounding issues. It's not that in reality it does add to 100%, but depending on how many digits you take it out to, it might be a tiny bit off. So I'm going to introduce bar chart first. because we tend to like them a little bit better. So a bar chart represents the categories, and then the height here, it can be the counts, or it could be proportion, or it could be the percent. So the bar height is count or percent or proportion, like with respect to whatever the sample size is. If you do have counts, the count total should add. So like it looks like, what, 25 here. I'd have to double check. Somewhere between 10 and 15 here, and so on. But they should add to 111 if I counted accurately all the bars. Percents should add to roughly 100%. Same comment I said about the frequency table. Depending on how many digits past the decimal that you rounded to, it might be slightly off. But if you didn't have any rounding at all, it should be exactly correct. It should be exactly 100%. So things that are neat, so you might notice on the x-axis are our categories. There's absolutely nothing forcing the categories to go in that order. Just note, by default, R likes to put them in alphanumeric order. So it would do, quite honestly, exactly what this one did. So XL was the first one alphabetically, then JMP, then Minitab, and then TI-84 is the last one alphabetically. R will do that by default for you. However, you can do things. There's a re-level function. You can force it to put it in order however you want. Maybe you want to see, the group with the highest and then have descending. Or you might have it the other way. You might want to see the group with the lowest and see it increasing. Totally depends on what you want to see here. But the idea is, because they're categories on the x-axis, it absolutely doesn't matter what order they're in. It might make more sense to put it in one order than another order for you, so go ahead and do that. But there's nothing really forcing the order. They're not numbers that have to go in a certain order, so you can reorder them. So examples here. These are years. They went ahead, they put them in order here. I feel a little iffy about putting years there, but yeah, but they also have them in ascending order here. Here they go ahead, this is a horizontal bar plot. They wanted to they're looking at risk of crash caused by type of distraction, so they have dialing phone all the way to managing personal hygiene. And they decided to put it in descending order. So here's the thing with the highest risk factor and then going down. And that's fine too. You might have a average daily step count per month and you have 5 individuals. You could reorder them because maybe you want to see who had the most versus who had the least, or you could just keep them in whatever order you want. One I tend to see is a Monday, Tuesday, Wednesday, well, I guess Sunday, Thursday, Friday, Saturday. People tend to leave days of the week in a certain order, although there's nothing actually dictating that you have to in a bar plot. So keep that in mind. Then pie chart, it's another really, really common tool when you have a categorical data. So each category gets a pie slice. So like R here is this reddish slice. They're supposed to be sized proportionally along with their category. So like R has the biggest proportion, so it's 0.306, and the next biggest one's like 0.225. It has, not quite a third of that pie. So it should have the biggest wedge. The counts, if you have them by counts, should add to the sample size. So if I add all these counts together, I should get 111. The percents should add to roughly 100%. So like I said before, depends on your rounding. Maybe it won't be exactly, but if you had the percents with no rounding whatsoever, they would absolutely add to 100%. So we do want to put a disclaimer on these. We don't like these ones as much as bar charts. They can be less effective. They can definitely be misleading. So they're extremely common, so we want to show them to you. But they can be a poor or misleading display. So what I mean by that, how can they be misleading? So all three of these pie charts are the exact same pie chart, but the angle I'm viewing it at versus the height that I'm viewing it at are all very different. So like if you even focus on just this yellow wedge, I mean, it probably looks pretty similar on the first two, but it does look smaller because of the perspective. So absolutely the dimension and the perspective and all of that of the pie chart can absolutely make it very misleading very quickly. So definitely something to consider. It's not saying, oh, we never like them, but I'm not even sure how to make a pie chart in R. I had to make these in Excel, which is embarrassing. Don't tell my colleagues I used Excel. Oof. But no, but really, we won't be making pie charts, but it is important to be able to look at one and to go, oh, okay, well, that has the biggest slice, so that has the most people in it. And this was fun for me. So just a quick way, if you want to go, okay, I have categorical versus quantitative data. If you have categorical data and you want to figure out like, oh, okay, well, what kind of plots can I use? Here's just a real quick, just a way to remember. So that show way back in the day, I mean, I know it ended, I don't know when it ended, How I Met Your Mother. So there's this character Marshall. I think he's hilarious. He was my favorite. You don't have to like him though. So they discovered printing, like poster printing at their work. So they started going just really, really nuts by printing a bunch of plots. So there's this example. Here's a pie chart describing my favorite bars, and here's a bar graph describing my favorite pies. These are the two. These are the two plots that we use for categorical. So if you're like, hey, which one is it? But you can remember this scene, there you go. And for me, I'm one of those people who, here's a really nerdy way to remember it. And if you do remember it, it doesn't really matter how nerdy it is. So there you go. Okay, so now we're wandering into quantitative variables. So histograms. They're going to look a lot like bar plots, but they are going to be a little bit different. We're going to poke at it. So it's a quantitative variable. So the big difference is going to be on the x-axis here, it's numeric. And it wouldn't make sense for me to reorder the bars anymore. It would alter the numeric nature of the axis. So we can actually set the width of each bar. Here we have bins of 10, so 30 to 40, 40 to 50, 50 to 60, and so on. You can actually specify in R exactly what sizes you want them to be, so that's something to consider. So then we have the observation in each bin. So like here, 30 to 40, it looks like I have one individual between 30 and 40. 40 to 50, I have one individual. 50 to 60, I have 4, and so on. So the bar height, a lot of times it'll be frequency. I mean, it could be proportion. Depends on the scenario. But yeah, it'll be some sort of count, proportion, on the Y, and then it'll be whatever it is that you're measuring. So this particular example is percent of students that stay in state during their first year of college. And it's rounded to the nearest percent. And that is my axis. I'm going to show you, like, if I wanted to put that particular histogram together. So here's my data set. It's looking here. In reality, there are only 2 columns, but it would be so long it would not fit on this page. So we stack them. So we have state here, and then the percent of their first year college students that stayed in state that year. So like Arkansas, no, oh my gosh, I know this. Alaska had 83% of their first year college students stay in state their first year. That kind of a thing. So we're going to go ahead and here are my bins. I have them roughly, so like from 31 to 40, 41 to 50, and all the way to 91 to 100. I stopped at 100 because you can't have more than 100% of people stay. I also started at 31 because our minimum, so Vermont had 36% stay. They only had 1. So you can absolutely include the bins from 0 to 10, from 11 to 20, from 21 to 30, but they don't have any observations. So just going through here, now I'm going to look at 40 to 50. Oh, just had 1 there. This is me totally cheating. I totally did all this ahead. It's so much harder if you're just trying to read through it. So 51 to 60 looks like 4. 61 to 70. So 4 plus 1 plus 2 should be 7. 71 to 80. There's more. There's 2, 6, 3, 3. Looks like 14, I think. Then 81 to 90. 5, 5, 5, 3. 18. And then 91 to 100, it looks like 5. So things to note, there are 50 states in here. If I added all these frequencies together, I should get 50. If I don't get 50, something went wrong. It's definitely a good indication that something got added incorrectly somewhere. So once, okay, here it is. So once I have that frequency table filled out, I could go ahead and fill it in here. So just note that I try to draw straight lines. I'm not great at it. So 30 to 40, we had 1 individual. Or, yeah, 1%, sorry. 40 to 50 was 1. 50 to 60 was 4. And I can do this for every row. I'll do it for 1 more. 7. So like that. And I can go ahead and fill them all out for all of them. So, boom. Okay, so I was close for handwriting it. So that would be essentially how I go ahead and I get my histogram. R will do this for you. It's got a great hist function, and it will make a histogram for you. And you can tell it exactly how wide, or how many breaks you want. There's a breaks option in there. So one comment I want to make is, if I use different bin widths, so instead of going from 30 to 40, 31 to 40, 41 to 50, maybe if I went 31 to 35, 36 to 40, 41 to 45, it could change how the histogram looks. So, for example, here's the one we just did, where we have a bin width of roughly 10, only because of how we rounded. But if I cut the bin width in half, it looks similar in shape, but there are things different. Like, I didn't realize, hey, that this was so low and this was so high compared to the other. So it absolutely changing your bin width can change how your histogram looks. Definitely worth keeping an eye on. It can absolutely change how you describe your histogram depending on what bin width you use. Like, you don't want to use a bin width that's so big that you just have like 100%, it's like one big rectangle. That's a horrible, like, if you make your bin width too wide, there are too few of there's only one bar. It's horrible. So stem plots, admittedly, this is one of those things that, like, I feel like they have you do in high school and maybe even middle school by hand. You can make them in R. I don't see them as often, especially with bigger data sets. These are ideal for small data sets. So you go ahead and you split, usually, like if I had a, I don't know, we're going to do that one though. If I had 38, it's almost like you draw a line between the ones and the tens place. So you would write, oh, this is 38. If I had, 153. I would have 15 and 3, basically. So this is my stem, this is my leaf kind of idea, and it's going to be organized like there's one vertical line. These are all the things in the tens place, and these are all the things in the ones place, and you put them in ascending order. So this is that percent of students that stay in state, and this would be my STEM plot. So I have 30, 40, 50, all the way through 90. Things to note is if I had something in the 30s and not the 40s, you would still write a 4 here. You would just have a blank here. You want to make sure that from the minimum to the maximum, you include all the 10s that are in between. So 36 is there, but there are 4 values here that are 80. So you get 80, 80, 80, 80, 81, 81, 81, 81, 81, and so on. And honestly, we tend to look at these almost sideways. This is almost exactly like looking at a histogram with a bin size of 10, but you have to turn your head to see it. So once again, a sample size of 50 is kind of big for a stem and leaf plot or stem plot, but it is doable. So I do see it. I just, admittedly, if you have a data set of over 30, most of the time you're going to use either a histogram or a box plot, and we'll get to box plots as well. So that's just showing 76 for Oregon. That goes in the 70 spot, and then it's one of the 6s. Honestly, it could be either of the other ones as well. So once you have these distributions, especially, well, yeah, a lot of times like histograms and box plots, but stem plots as well, there are going to be 4 main points that you talk about. You want to talk about the shape. So we want to know, hey, is there some overall pattern? Is it nice and symmetric? Is it skewed to one side over the other? Is it unimodal or multimodal? So it's talking about like how many peaks does it have? Does it have 1 peak? Does it have 2 or more? We start usually getting a little upset if it has 2 or more, but it's worth noting if it does. Where it's centered. So do we have the bulk of observations in one spot? Do we have a peak that we could talk about? A lot of times we'll talk about the mean or the median to try and describe the center of the data. The spread. So we might talk about the range, the IQR or interquartile range, which we will talk about more in, I don't know if it's this lesson, but maybe the next lesson, and the standard deviation. So if we give you a plot only, chances are the range is what you can talk about. Like for this one, I can tell you, oh, all the values, they go from 30 to 100 if I only had the histogram there. And then outliers, tell us about those weirdo points. Is there a point out there that's like off on its own? Like what is it doing? Like tell us about it. Hey, we have a high outlier, we have a low outlier. And we do have criteria like for actually determining, hey, is this value an outlier or not? But once again, like it's something we'll get to. This is more of like, let us know if there's an oddball point. So for this data set, the percent of first-year college students that stay in state is negatively skewed. So, and we'll talk about what we mean by skewed. So this is left skewed. You can also think of negative. So what it means is we have a tail that's longer on the left side. Ranging from, and this is me knowing what the min-and-max are, so ranging from 36% to 92%, with a lot of states hovering around 80. So we know the center's somewhere around here, so if you said, hey, it's between 70 and 90, I'd be happy with that. And you could say, hey, there are a few low observations around 30 and 40%, so you could talk about these seem a little low. So getting to shape. So we're going to talk about symmetry, and we're also going to talk about how many peaks. So symmetric or skewed. So the idea of something symmetric, you could draw a line down the middle, fold it in half, and it's roughly the same on both halves. It doesn't have to be exactly, but it does have to be at least like roughly the same. So if you wanted to draw your, like use your hands, you can hold your left and right in front of you like that, and that would be symmetric. If you have a nice bell-shaped curve, like the normal is symmetric. Skewed, that's when you start having this tail. It's almost like somebody pushed it over a little bit, you know? So you have a left tail, so this is left skewed. If you're holding your left hand in front of you and pretend that your left thumb is the tail, that it would go with left skewed. Similarly, if you put your right hand in front of you and pretend that your thumb is a long like right tail, that would be right skewed. So right. So yeah, if the tail is longer to the left, it's left skewed. You can call it negatively skewed. Most of the time I'll try to stick with left skewed. If it's longer on the right, it's a right skewed or positively skewed. Once again, I'll try to stick with the right skewed terminology. That, or I like to include both. I don't like to just include negative or positive. That's a little confusing sometimes. Okay, so unimodal or multimodal, it's saying how many peaks are there. So like here, wanted to fit, and it's not the most excellent fit, a density curve to it. It has one peak. So like this bumpiness, I'm not concerned about this. I would still fit like one curve, something like that. Bimodal, so I'm not like concerned about bumping here, but I am concerned that, that bumpage. So when we think bimodal, think Dracula's hairdo. You know, that one from the 90s with Keanu Reeves? That's what we mean by bimodal. We're not worried about little bumps like this. We're worried about big bumps like that. Okay, that's what we mean by bimodal. So we're asking how many peaks. So you can use unimodal, bimodal, multimodal, or you can just describe how many peaks there are. So, for example, we have the player weights in pounds for 2015 football season for the Seattle Seahawks. So if you look at these weights, probably argue they're fairly bimodal with modes centered at, and they say, okay, well, one is around 215, the other is around 300. The overall weights range from 175 to 350. The typical weight's most likely around 240, so somewhere around here. And I'm okay if you say, oh, the typical one, it's probably between here and here. Most of the time, if it is bimodal, we're not going to be too concerned with you giving us all the same information as usual. If you tell us it's bimodal and tell us where both of the peaks are, that tends to be as far as like, it's a lot harder to figure out what the typical value will be. But if it's unimodal, absolutely, we'll want all of that information. Absolutely. So that was lesson 17. We're going to get on to data summarization, measuring the center, and then the spread, and then we're going to pull some of that together and make a box plot towards the end. So we'll see you for that.